Okay, so now I'm going to do a quick video on collision density. This is actually introduced in Focus 1B, but we skipped Focus 1B because we weren't really going to use it until we got to kinetics. And so, excuse me. And so you can go back to learn about gas laws and stuff, and you can find collision density there. What is it? Okay, so A is going to smash into B. So they're going to smash into each other. Actually, I should draw arrows this way. Okay, so they're going to smash into each other. What the collision density, which is represented as a Z sub AB, if A and B are going to smash into each other, is equal to the number of collisions between A and B divided by the unit time and a volume. Cool. So you're going to have A and B. It's the number. So if you have a box of A's and B's, it's been a while since I've drawn a box with particles in it. Okay, and they're all bouncing around. Then you count. So you have your stopwatch and you say, okay, for say 5 seconds, I'm going to count the number of collisions that happen per that 5 seconds per that volume. So here's my volume value. So some box. But then you want to say, okay, how many collisions happen per time? But then you actually want to multiply by a time increment. Okay, so you want to know, well, how long is the duration of time that you're measuring over? So that's the idea behind the collision density. The actual number, ZAB, is equal to, get this, the cross section. It's also equal to the relative mean speed of both A and B approaching one another, which is 8 kT over pi mu, all of that quantity to the 1/2, where mu is the reduced mass. So this is the mass of A plus the mass of B divided by the mass of A times the mass of B. And if you, so you may have seen reduced mass before if you took my quantum class. If not, welcome to the reduced mass. The units of this are going to be in mass. And so a lot of times my students will forget which one goes on top, the added or the product. But if you think about it, those are going to have the same units. That's going to be mass squared. And so, oh my gosh, wow, see, I got it backwards. It should have the units MA times MB divided by MA plus MB. Oh my goodness. Week 9. Anyway, case in point, if you do it wrong, the units will tell you which is the right one. So this becomes grams squared divided by grams, because adding is going to give you grams. Grams cancel, and so you're left with grams. Yay, mass. Anyway, unit analysis saves lives, I promise. Okay, so ZAB is equal to cross section. This, which comes from kinetic molecular theory, where temperature to the 1/2 divided by molar mass. But this is going to be the combined mass or the reduced mass of that. The number of particles you've got, Avogadro squared, multiplied by your concentration. Okay, so this is collision density. And the cross section, again, can be calculated out. So cross section is equal to pi 1/2 dA plus 1/2 dB squared, where that's the half the diameter of each A and B from the last video. Cool. So real quick, I want to show you an example of numbers of the collision density. And so for N2 at room temperature, this is nitrogen. So what is that? 80% of our atmosphere, mostly nitrogen. Only about 20% is oxygen with 1% argon. So nitrogen at room temperature, it's about 65 degrees in my house right now, so a little less than room temperature. But the cross section is equal to 0.4 nanometers squared. That's cool. D is equal to 280 picometers. Now this D is then the same thing. So if you have a nitrogen N2 and an N2, so this would be this value. So that D, so that's 280 picometers between nitrogen and nitrogen hitting one another. And then Z, the collision, the number of collisions between A and B per unit time per a certain volume. Get this, ZAB is equal to, and this would be of nitrogen and nitrogen hitting each other, which most of the time doesn't yield a reaction, if at all, is 5 times 10 to the 34. Holy, that's a big number. Inverse meters, inverse seconds. So the number of collisions, it's not going to have a unit per time, per second, per volume, per meter cubed. So in a meter cubed, how big a meter cubed is, 5 times 10 to the 34. To the 34. That's bigger than big. Let's think about big. The mole times 10 to the 23rd. Okay, back to orders of magnitude. So we know that a mole is 6.022 times 10 to the 23rd. You really should just say times 10 to the 23rd because the 6 part doesn't matter because times 10 to the 23rd is the important part. If you were to take a mole of seconds and count 1, 1,000, 2, 1,000, 3, 1,000, how long would it take to count a mole of seconds? So the age of the universe is about 15 billion years old. And I believe it would take 1 million universe lifetimes for a mole of seconds. So not just one universe lifetime, 15 billion years, 1 million, possibly 100 million. I need to go back and redo the calculations. It's been a while since I've done this example. But we're talking a crap ton of seconds. That's times 10 to the 23rd. This is times 10 to the 34. And it's not just, 23 to 34. That's only, what is that? 11 more? No, this is huge. So huge. The number of times that you have a collision in this box of the nitrogen in the air right now. So you can smell it. Well, you can't smell it, but you inhale it. So that is so many collisions. Gas phase. Okay, cool. So that is collision theory and then collision density. Next video, we're going to move into exactly what I just introduced you to, which is diffusion controlled reaction. So we're going to move into liquids and we're going to talk about what things are driving intermolecular forces that yield reactions in the liquid phase. And how do we quantify that in terms of kinetics? Go team.